Hello everyone, this is Indradeep Kumar, Assistant Professor, IARE, Hyderabad. In this video, we will see beam deflection by a uniformly loaded cantilever by the method of complementary energy. So now in this, we will see what a beam, cantilever beam is there, which is simply supported. That means UDL is uniformly distributed load is applied on that one. Then what will be the deflection by the energy method? So this is the question. That means this figure shows uniformly loaded cantilever of uniform cross section and length L. The uniformly distributed load W per unit length produces a vertical deflection V, which are required to find. So now just see here this vertical deflection, that is this delta T, actually this delta T, that vertical this deflection we have to find. So now what we will do, so this see here, this is the uniformly distributed load is distributed, means initially this was here, actually this should be here, that means the cantilever. Once we applied the cantilever of the weight W per unit length in over the entire span of the cantilever, then what happened? Because of this load, some bending will be there. That how much bending will be there, that we have to find. That is how much deflection will be here. So that just assume that delta T is the deflection from this to this one. Now only we have this load. So for energy method, what we are doing, we are applying a fixous load. So let's apply the fixous load at the end of the end point of the cantilever. Okay. Then next, what we will do here, just take the cross, that means at a distance Z, take a cross section or of delta. This one, this is just thickness of that one. How much deflection is there at this? The deflection is delta, means at a distance deflection. So total length of the beam is L. So once we find this deflection, then we can integrate from here to here, 0 to L, we will get the total deflection. So this delta T is the total deflection. Okay, so that we have to find. So let's see. The fixous load method of the framework example may be employed in the solution of beam deflection problems where we require deflection at positions on the beam other than concentrated load point. So where that concentrated load point will be there, means in this concept what we know, or here when UDL is there or any UDL is there, that is uniformly distributed load over the entire length L, then we are assuming, means this overall effect of the length is acting at the half of the length, means at the center of the length or beam size. So means this will act at where? At L by 2. So now in this case what we have to do, means we cannot take at L by 2 distance that fixous force. So other than anywhere we can take. So let's just at this point we are taking, we can take here also, that is not the issue, right? From there you have to take the distance, that is simple. So it's not necessary that at the end point only you can take to solve that fixous load, maybe anywhere, right? So suppose that we are to find the tip deflection, that delta T, this is that T, that stands for delta T of the cantilever of the previous example, in which that previous example, that what we had seen. So just see, I'm just recalling this previous example once again, right? So just because of this one load is acting at the tip itself, means there is no other load, only the point load is acting at the tip, and because of that the vertical deflection is delta V. So now in this case what we did, we assumed at a distance x some delta thickness, then we found the radius of gyration because we required what? Dou theta and dou m by dou p, that we require. So first we found dou theta, like, yes, so this is the energy equation, right? For this one, for point load, so just here this d theta and dm will be there because of this point load, this will be the energy in that one, right? So the same way you have to use after differentiating what we got in that one, this one d theta dm by dp. Similarly we have to find for which one, that for the cantilever also. In that also we had seen dou theta equals to k dou z, right? Where d theta is what? 1 by k Em by m. So dou theta is nothing, just k. K is what? From here 1 by k you can see E I by m, hence k will be equals to m by Ei. So just substitute here. So dou theta will be equals to m by Ei into dou z. M by Ei into dou z. So this is just for d theta. Now after that what we have taken? That we are taking moment. After that difference is because m dou p dou m by dou p we required. So now differentiate with respect to p. So that after that we got z. Now for the vertical deflection, just substitute in this formula. We substituted in this formula, right? The same way we will do here again. So the same concept we have to use, right? That in the previous one. In which the concentrated load had been replaced by a uniformly distributed load of intensity W per unit length. Means now in this case that concentrated load or point load is replaced by the uniformly distributed load. And we assume what? One fixed load acting at the tip because we are finding deflection at that point, right? In previous case we didn't assume this one. Why? Because at this point already force was there. It's not required that fixed force we need to add. In previous video also we had seen where we have to find the deflection. At that point we are applying the fixed load by removing all the forces. But in that case their force already it was there. But in this case this force, the overall effect of this weight will act somewhere at the center of this rod, that at L by 2. So at this point, that is at the tip, we assumed that one fixed force is acting and overall the tip deflection will be delta T. So now because of all the forces, whatever the forces is acting, we have to find what? Moment. Okay, so now just see. First we apply a fixed load PF at the point where the deflection is required. So here this concept again we will use where the deflection is required at the tip we are finding. So put fixed load at the tip. Fixed load is what? PF. So now after that what will be the total complementary energy of the system? C will be equals to 0 to L of over that means overall length or over entire length, 0 to M moment d theta dm, right? This is because of moment. This is because of what? Fixed force. So delta T, tip deflection is delta T and PF forces acting on that one. So delta T into PF will be the energy. And next because of the overall weight. So 0 to L delta W dz. So just see here that we assumed here at this point. For a small length, a small weight is there. So over then once we will integrate for the 0 to L, then we will get the total weight acting on that one, that is per unit length. Where the symbol take their previous meaning and delta is the vertical deflection of any point on the beam. So delta T is the vertical deflection or what? Tip deflection of any, that means delta is just a vertical deflection at any point and delta T is the tip deflection. Then next step what we are doing after this, we have to find what? dc by d what? P. So next step same we will do. dc, that is del c by del pf will be equals to what? 0 to. So another this integration symbol will get cancelled, or let me write here first. So what we have, c equals to integration 0 to L, right? Then here you just see 0 to M d theta dm, 0 to M d theta dm minus integral of what? Delta T PF. So simply delta T PF minus next will be what? Integral of 0 to L delta W dou Z. This is there. Now what we required? Dou C by dou PF. In this case the difference is only what we have to do. We have to differentiate with respect to PF. Okay. So now what we will, after differentiating, what we will get? Dou C by dou PF, because once we have the fixed force we have to differentiate with respect to the fixed force. In previous problem fixed force was not there, direct the concentrated force was there, that load, so we differentiated with respect to that one. But here we are applying the fixed load, so means here you have to differentiate with the fixed load. So just keep in mind, that's why again I recall the previous question. Okay, now this will give what? This differentiation will get cancel after differentiating. Differentiation and integration is reciprocal, so this will get cancelled. What we will get? 0 to L d theta dm by, that is, or dou m by dou pf, minus here that pf, this becomes 1, so delta t. What about this one? This is constant, there is no delta pf, so this will be 0. So means for this we can write 0, right? So this is our differentiation. Now what is there for the equilibrium, or the this must be equal to 0 for at equilibrium. So delta c by delta pf is equals to 0 to L d theta into dou m by dou pf is minus delta t equals to 0. So from here what we will get? Delta t equals to 0 to L d theta dou m by dou pf. This we will get. Now here we have to find what? D theta and dou m by dou pf, and then we can substitute. So d theta already we found, that is m by ei into dz. How? In previous video I explained, but again I am explaining here how to find this one. So that radius of curvature was 1 by k, which is equals to ei by m from the bending moment equation. Okay, so this is 1 by k, and now 1 by k was the radius, right? We know that theta equals to L by r. Here theta is what? Dou theta or d theta equals to L is here d z by 1 by k. So from here we will get d theta equals to k into dz, right? Now what is k from here? Take reciprocal, so k will be equals to m by ei. So substitute here, so d theta equals to m by ei into dz, right? So this is d theta. From this we will get. Now what is required? We have to find dou m by dou pf, right? So next what we will do? We will differentiate. First we will find the moment, how much moment is acting on that one, and then we will differentiate with respect to the pf. So now moment, because of the fixed force, will be what? At a point z we are finding. So see the figure here, this is pf at a distance z, so this will be pf into z. Now because of this uniformly distributed load, so their weight is what? wz for this much length, right? Divided by, and where it's acting? At the center of this one, so into z by 2, that distance. So this is the total weight where it's acting at z by 2. So this becomes wz square by 2, right? This is m. Now so this is m. Next, when we will differentiate this one, what we will get here? So differentiate with respect to, so let's see, this pf is not 0. This pf is, later we will add this as a reference to 0. Here if you will put 0, then everything will be 0. So this pf is just for fixed load, what we will assume as 0, right? So m equals to what? After differentiating, what you will get? What we have? M equals to pf into z plus wz square by 2. So this term there is no, now we are differentiating, so dou m by dou pf, right? For this term there is no pf term, so this will be 0, only the differentiation of this one. So differentiation of pf into z, differentiation of pf is 1, so z into 1, that is z. So now we have dou m by dou pf is equals to z. So now we have d theta, we have dou m by dou pf. Now substitute in the deflection, that delta t equation. So now what we will have? So let's see here. So now from here what we will get? Delta t is equals to 0 to L d theta into dou m by dou pf. So this will be there. Right, now substituting the values. So this equals to 0 to L, d theta is m by vi into dz. Okay, into dou m by dou p, what we got? Z. So dou m by dou p, f here is z. So into z. Okay, now m by ei. M again we can change in terms of p. Why? Because m is not constant. So here we have to replace this whole m to this one. But in that case, only this pf will be 0. Right. So let's change first, or take 1 by ei constant. So 1 by ei constants out of integration. Integration 0 to L. Now m is what? P, replacing m to this one. P f into z plus w z square by 2. This whole into dz, because m dz, so I've just replaced with m, and this another z is left. So now here put what? Because we assume that fixed force, in that finally what we are doing, we are putting pf as 0. So now after this 0 into z, that becomes 0. So this will be what? 1 by ei 0 to L. Now this term becomes 0 after putting p of 0. So what we have? Wz square by 2 into z into dz. So what we can write after this? So this becomes wzq by 3. Sorry, wzq by 2. So 0 to L wzq by 2 dz. So now we can integrate it. How? Right. So this will be what? W by 2 is out of the integration, and integration of zq is what? Z power 4 by 4 and 0 to L. Okay. So now after putting the value W by 2, this will be what? L power 4 by 4. So this will give you W L power 4 by 8. So WL power 4 by 8, and that already we had taken that EI constant. So that EI. So EI means what we have? Vertical deflection delta T is equals to WL power 4 by 8 EI. Clear? So now after substituting the value of d theta dm and d theta m and dou m by dou pf, and then putting what? Pf equals to 0. What we will get? Delta t equals to wzq by 2ei, and after integrating and substituting, we will get value wl power 4 by 8ei. That already I showed you. So now it will be noted that here, unlike the method for the solution of the pin joint framework, the fixed load is applied to the loaded beam. So there we are assuming, but in this case what we are doing, already it's loaded and then we are applying the fixed load. There is however no arithmetical advantages to be gained by the former approach, although the result would be obviously be the same, since m would be equals to z square by 2. Means whatever the former, without fixed load there is no advantages over that one, because anyhow the moment we are getting same, and that will be equals to wz square by 2. And here also after substituting here pf as 0, we are getting same wz square by 2. So there is no difference. Means with this also we can find, already we had seen the advantages of the energy method, means complementary energy method, means wherever that earlier method is not applicable, or for indeterminate structure also, we can use this formula and find the deflection of that one. Okay, and dou m by dou pf would have the value z. So with that also we can say that there is no, means either former approach, there is no much, that means there is no disadvantages over this one. Anyhow moment will be z square by 2. So just quickly I am recalling once again. So first what we have to do, just in question it's a given, it's a simply that a cantilever beam is there on which W per unit length is spread. That means that is loaded by W unit per length, right? For that, we have to find the deflection because of this uniformly distributed load. So next, what we did, we assumed, because at the point where we have to find, we required a Fixious force, right? So here it's not there. In previous question, it was there at that point itself, so we didn't add it. But in this case, we are adding one Fixious force. Later we will put 0 because we are assuming here the Fixious force is acting. So after putting the Fixious force, what we have to do, whatever the deflection is there, that we have to find. So our first target will be what? Find d theta. Already explained how to find d theta. Next, dou m by dou pf. In this case, dou pf, because with respect to pf we have to find. We applied the pf. So next, this will be the energy equation, right? So this will be, because of the moment, dou theta, dou m, then delta t pf, that is vertical deflection at tip, into pf because of the Fixious load, minus 0 to L for 0 delta w into dz. So this is because of the uniformly distributed load. So now all the load we consider. So this time this also we have to consider. Right, in previous case this was not there, only the P was there and this uniformly distributed was not there. But in this time, because that is varying with the length, so we have to take from 0 to L. Right, after that, next what we are doing, we are differentiating with respect to PF. Remember, here you have to differentiate with respect to PF, not like the point load. In that case, we simply differentiated with P, not PF, because they are already at that point P was. So after differentiating, we got this one. Again, that must be equals to what? For the complementary energy, it should be in equilibrium. That must be equals to 0. So after this, what we will get? Delta T. Delta T will be equals to what? What we got? Equals to d theta into dou m by dou. D theta we already found. Now next, what? First we have to find m because of the forces. So because of the PF into z will be the moment at a distance z, and same at a distance z because of the uniformly load w into z into z by 2. Z by 2 will be the distance where it's acting. So wz square by 2. Now what we have to do? We have to differentiate this with respect to PF to get dou m by dou PF, what is required here. Right. So after differentiating, what happened? This becomes simply z, and this term there is no PF, so hence this is constant and that becomes 0. So now we have dou m by dou PF. Now substitute that d theta value and dou m value in delta t. Right. After substituting, you will get delta t equals to, here again you have to replace this m, right, with the pz, because in this formula this d theta dou m by dou pf is there. So m is there, so replace this whole m and then differentiate, you will get this one. Okay, because here this d theta is required, right? So that also I explained what that means. Here first d theta, okay, d theta what we have, m by ei dz into z, right? This is 0 to L. So this m we have to replace. Don't forget to replace the m and don't take constant, right? If you will, m is not constant, m depends on the length. So if length will vary, m will vary. So first we have to change this in terms of the load. So what we will do? 0 to L, m is what? This one. Change this, whatever m we got, replace here. So m pf into z plus w z square by 2. So this is the value of m divided by ei, you can keep here also or out of the integration, and dz, right here. This is for theta. Now what we got? This dm by dps 0. So now here you have to put this 0. Earlier also I explained. Now what we have? wzq by 2ei, that we got here. wzq by 2ei. After integrating and substituting the limit, what you will get? wl power 4 by 8ei. Okay, so for this you can refer the Maxon book, that HG Maxon Aircraft Structure for Engineering Student. There you will get this derivation. So if you have any doubt, you can just comment on the video or you can contact me regarding the doubts. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.